Welcome back to this past paper walkthrough for O-Level Computer Science. This is from Syllabus 2210 and it's for the October-November 2023 paper. This is for part 1, the first 7 questions out of a total of 13. So, everybody, as you know, those people doing the O-Level are going to be sitting 2 papers. This is paper 1, 50% of the final mark, 75 marks in total, 1 hour and 45 minutes for this paper. Okay, all questions compulsory. You are not allowed to use a calculator and this will be externally assessed. Paper 2 weighted the same way and for the same marks. Okay, but paper 1 generally comes first in the exam calendar. Here we go. As I say, it's 2210/12 for paper 1. Okay, and it's from October-November. So let's get started. Okay, question 1. Malware can be used to corrupt data stored on a computer. Okay. Tick one box to show which cybersecurity threat is not a type of malware. Is it phishing, ransomware, virus, or worm? Well, all of these, ransomware, virus, and worm, all are sort of software that gets installed on your computer, whereas phishing isn't. Phishing's a link, usually an email link, that's sent to you, and then it's got some bogus links or a bogus link to a website that tries to steal your information, be that your credit card information, your name, address, and personal details. Okay, so the answer there would be phishing. Okay, some people call it phishing, some people call it phishing. Part B, identify one other example of malware than those given in part 1A. Okay, so what we've got, Trojan horse is a good one, adware, okay, and maybe something like a keylogger. So any one of those, keylogger, Trojan horse, adware. Part C, identify the type of software that is used to find and remove malware from a computer. Well, you could put antivirus software, but really, because it says malware, I would put anti-malware. Okay, anti-malware. This pen's a little bit a bit weird. Next part, part 2. A register stores the binary number, so 111-00011. Give the binary number for the binary number stored in the register. Okay, fair enough, we've got working space there. So let's put some numbers across the top. 1, 2, 4, 8, 16, 32, 64, 128. So we've got to add all these ones together. So 128 plus 64 equals 192. Okay, so that's got those two, 192. Plus 32 is 224. Plus this and this, plus 3 equals 227. Switch back to red. So the answer is 227. Okay. Part B, give the hexadecimal number for the binary number stored in the register. Okay, so part B, give the hexadecimal number for the binary number stored in the register. Okay, so let's write this number down in our working space. So the number is 1110011. Okay. Now I'm going to split this into 2 nibbles, like so. Okay, and then I'm going to add these numbers up. So I'm just going to put in some little numbers here. 1, 2, 4, 8. 1, 2, 4, 8 for our 2 nibbles. Okay. Now this first side is 2 and 1 equals 3. And the second side, 8 plus 2 plus 4 would be 14. Now we know that 14 doesn't work as an hexadecimal number because 10 equals A, 11 equals B, 12 equals C, 13 equals D, and 14 equals E, with 15 equaling F. So the answer would be E3. Okay, so I'm going to write in here E3. Okay. Now part C, a logical shift of 2 places is performed on the binary number stored in the register. Complete the binary register to show its contents after the logical shift to the left. So let's put our original number back in. 1, 1, 0, 0, 0, 1, 1, 1. Okay, and it's going to move 2 spaces. 1, 2. So this number here, this first one, is going to go there. This second number is going to go there. And then I've got 1, 2, 3 zeros. That's these 3 zeros here. 1, 2, 3. Okay. And then this one here goes there. Now don't get confused because these ones don't go and loop back round. No, this just gets filled with spaces there. So the new answer would be 1, 0, 0, 0, 1, 1, 0, 0. That's how that would work. Okay. Part D. The negative denary number minus 99 needs to be stored in the register. Complete the register to show the binary number that would be stored using 2's complement. Show all of your working. How it works in a register, we have 1, 2, 4, 8, 16, 32, 64, minus 128. Okay, would go in there. So when we begin, we'd have one of these numbers here. Okay, that would signify minus 128. Now, every time we add one of these numbers, okay, this leads us up to minus 99. So, for example, if I go minus 128 plus 64, yeah, that gets us to minus 64. Okay, so that's no good because we've got minus 99. So we've got to work out what's going to get us to 99 using these numbers here. So let's go and rub that out. So as you've just seen, it's not going to be 64. If I take 32 away from 128, I'm going to get minus 98. So that's no good either. So I'm going to take that off. Okay, but if I take 16 away, I'm going to get minus 128 plus 16. Okay, I'm going to end up with minus, so I'm basically taking these away, 2, 1, 1. I'm going to get minus 12. Okay, if I do another one, I'm going to get minus 4. And if I do another one, I'm going to get minus 100. Okay, so 16 plus 8 plus 4 equals 28. Yeah, so I'm now on minus 100. Yeah, but I've got to get to minus 99. So it's not going to be 2, it's going to be the 1. Okay, so minus 99, minus 100 plus 1 would be plus 1, yeah, would be minus 99. That's how it would work. So we put the 1 in the first column, that's minus 1, 2, 8, and then the rest of the numbers 0, 0, 1, 1, 1, 0, 1. Okay, that's how I would do it. Now we've got part E, where we're going to add two numbers together. Add the two 8-bit binary numbers using binary addition. Okay, give your answer in binary, show all the working out. So let's put these together. We'll do it like this. 0, 0, 1, 1, 0, 0, 1, 0. Okay, and then we've got 1, 1, 0, 0, 0. Try and get them as lined as best you can. Okay, so the first one would be 0 plus 1 would be 1. 0 plus 1 again would be 1. 1 plus 0 would be 1. 1 plus 0 would be 1. 0 plus 0 would be 0. 0 plus 1 would be 1. But 1 plus 1, this is where because we can only have 1s and 0s, remember, in a binary register. So 1 plus 1 would be 2. So 1 plus 1 would be 2, which means 0, carry the 1. 1 plus 1 again would be 2. Yeah, 1 add 1 is 2. So that in binary would be 0, 1. So now we've got a what we call like an overrun, whereby we're no longer in an 8-bit register. We've moved on to 9 bits. We have now 9 bits. There is an overflow. Okay, so that would be the number. Question 3. A user's computer has a central processing unit, a CPU, that has a clock speed of 2 GHz. She wants to change it to a CPU that has a clock speed of 3 GHz. State what is meant by clock speed. Well, clock speed, it is the rate at which a microprocessor executes instructions. Okay, and it's measured in hertz. Okay, it is the rate at which a microprocessor executes instructions measured in hertz. Okay, that was gets 1 mark there. Part 2A. Explain the effect this change will have on the performance of the CPU. Well, it will boost the performance by enabling more instructions to be executed per second. It will boost the performance by enabling more instructions to be executed per second. Okay, so the performance will be better. So tasks should be performed faster. Okay, I think that will do. Part B. The CPU contains a memory address register and MAR. Describe the role of the MAR in the fetch, decode, execute cycle. Okay, well the MAR holds addresses. That's what it's a memory register. It's an address register, so it holds addresses of the memory location that is to be read from or written to during the fetch execute cycle. It directs where data is to be fetched and stored. I'll put that in first. Directs where data is to be fetched and stored. Okay? So because it holds addresses of the memory locations. Holds addresses of the memory locations that is to be read from or written to. So directs where data is to be fetched and stored, holds addresses of the memory location that is to be read from or written to. The CPU, part C, the CPU has a list of all the machine code commands it can process. State the name of this list of commands. Well, this is list of commands. It's called the instruction set. Okay, the instruction set. And that would give us 6 marks, question 3, 6 marks. Okay, a washing machine is an example. Question 4, a washing machine is an example of an embedded system. Give 2 characteristics of an embedded system. Well, 1, it performs a dedicated function. Okay, does a specific job to do with a particular device, such as a washing machine. So it performs as a dedicated function. It also has a microprocessor. And we can go on to the cheap to manufacture. Because they're usually going into sort of white good or household items. Some companies such as Samsung, where they're going to be manufacturing thousands and thousands and thousands of products. So yeah, usually cheap, and as I say, they perform a dedicated function, and it has a microprocessor. Okay, I think that will do. Okay, part B. So let's look at this one. Part B. Circle 3 other examples of an embedded system. A little bit vague this, but let's have a look. I'd first of all say a vending machine, because that's got like a little, anything with like a little screen on it where you're sort of putting items in. So you would have an embedded system which is basically a little screen where you would put some numbers in, and the numbers would control which item in the vending machine would be brought forward and given to you once you've made a purchase. Okay, so a vending machine would be a good one. Laptop, no. Personal computer, no. Web server, no. Smartphone, no, not really. A security system would be a good example as well. Again, you've got a touch screen panel on there, which would enable you to sort of control when and the timings of the security system, when it should be turned on, when it should be turned off, and program it to do a specific job, such as zones in the house and various other things. And the third one's a bit tricky. I would, though, say a freezer. Because again, a modern freezer would have some kind of system in it. It could be just a series of dials, which temperature maybe controls an ice dispenser. So that would have a very, very simple embedded system. Okay, so there would be my 3. And that is question 4 complete. Okay, question 5. A band is recording the new song. They need to consider the sample rate and sample resolution of their recording. Give 1 benefit of using a high sample rate to record the song. Well, 1 benefit, basically, using an high sample rate to record the song captures more audio detail. Okay, so it's resulting in better sound quality and more accurate representation of the original performance. So that would be like a full answer, but it's only wanting sort of 1 benefit. So I would say better sound quality. Just going to switch to red. Better sound quality. Okay. Give 1 drawback of using high sample rate to record a song, and these are only worth 1 mark. So obviously better sound quality, but it's going to be a larger file size. So larger file size needs more storage. Okay, and that, of course, if you're emailing that to somebody or if you're sending it across a network, it might be a slow process. Now, for 2 marks, describe, what is meant by sample resolution. Okay, well, sample resolution is also known as bit depth, known as bit depth. Okay, known as bit depth refers to number of bits used to represent each audio sample. Each audio sample. Okay, high sample resolution, better sound quality. High resolution, better sound quality. Okay, so number of bits used to represent each audio sample. That is a sample resolution. High resolution, better sound quality. And part D, just move this up a bit. The band wants to compress the sound file, but they do not want any data to be permanently removed. Okay, identify the compression method that should be used. Well, there are only 2, lossless or lossy. Now, lossy obviously gets rid of information, whereas lossless is the one you would choose because it doesn't get rid of anything. Okay, so lossless compression. Okay, question 6. Let's move this up a little bit. Question 6. The table contains descriptions about data transmission methods. Complete the table by identifying which data transmission methods are being described. Okay, data is transmitted by a single wire, okay, 1 bit at a time in one direction. In one direction, well, that's serial, and because it's in one direction, it's a single wire for serial, and then it would be simplex, okay, rather than being duplex. Okay, data is transmitted down multiple wires, okay, well, that's going to be parallel, Now, multiple wires, multiple bits at a time in both directions, but only one direction at a time. Okay, so it's not full duplex. So it's not full duplex, one direction at a time. It's going to be parallel half duplex. Okay, so serial simplex, parallel half duplex so far. Okay, data is transmitted down a single wire. Okay, serial again, 1 bit at a time in both directions at the same time. So we've got serial, full duplex. Okay, and then finally, data is transmitted down multiple wires, multiple bits at a time in one direction only. So that would be basically the process of elimination would be parallel simplex. Okay, parallel simplex. So we've got serial simplex, parallel half duplex, serial full duplex, and parallel simplex. That would give us the answers for question 6. Question 7. A train station has a ticket inspector who checks each customer's ticket before they are allowed to get on the train. Okay. The train station wants a system that will allow the tickets to be automatically checked. Identify 2 suitable input devices that could be used to automatically read the tickets. We're talking about things like barcode scanners, QR code scanners. So I'm going to put in there barcode scanner, and I would put QR code scanner. Okay, they're the 2 I'd use, but you could say a digital camera. A digital camera could be an option as well. Okay, and then 7b, the train driver pushes a button to close the train door when all passengers are boarded the train. The train door will only close when there are no passengers in the doorway. The system to check there are no passengers in the doorway uses a sensor and a microprocessor. Explain, we've got a sensor question here, look. Explain, and it's usually for a lot of marks, 6 marks. Explain how the sensor and the microprocessor are used to check whether the train door can be closed. Here I would be using at least 6 bullet points for this. At least 6 bullet points. Talking about the analog to the ADC, talking about the DAC, talking about different sensors that you could use, okay, and an actuator to control the movement of opening and closing the doors. So I'll put all that as a bullet point. Okay, so let's have a little think about this. I'm going to draw the train doors, okay? Now on the train doors, explain how the sensor and the microprocessor are used to check whether the train doors can be opened. Well, we need some sensors, don't we? We need some sensors here. So maybe a sensor and a sensor here. Okay, what kind of sensor? Okay, so we've got either an infrared or a proximity sensor on the doors. Okay, measuring whether they're open or closed, or whether there's anything inside, i.e. a person, yeah, where the doors are. Okay, so to be used to sense person. Okay, so that would be the first job. That would be number one. What else? 2. Sensors send digital data we can put via ADC to a microprocessor. Okay, check data against stored data. Okay, so that would be 2 and 3. So the sensor sends digital data via an ADC to a microprocessor, check data against stored data. Basically, stored data being an empty space that the train doors have got there's nothing there. And then 3, if data matches, okay, stored data, signal can be sent to actuator, an actuator to close. Okay, so that would be good. If data not matching, doors remain open. If data not matching, doors remain open. Okay, alarm sent to driver. Okay, alarm would be sent to the driver. So I just move that up a bit, and then I'd put process repeats until the doors are clear. Okay, so excuse my writing. So let's go infrared. So let's recap. There's infrared or proxy sensors on the doors to be used to sense a person. The sensors send digital data via the ADC to convert it from analog to digital data to the microprocessor to check the data against the stored data. If the data matches the stored data, the signal can be sent to an actuator to close the door. Okay? If the data is not matching, the doors remain open, an alarm is sent to the driver, and the process repeats until the doors are clear, and then the doors can be closed. Okay, so that would get you 6 marks for that question there. That's going to be it for this video. Question 8 to 13 we will do in a part 2 video, because I think we're already about 25 minutes in. So thank you very much indeed, and I will see you for part 2. Bye for now. Please continue to ask questions, leave your comments, hit notifications, and please subscribe. And finally, if you wish to buy me a coffee, I'd be truly grateful. Please visit buymeacoffee.com/learning zone. Thank you very much indeed. See you next time. Bye for now.